Let's talk about the energy involved in breaking and creating bonds. Now, if you watched the other video, they had talked about being able to, before you can react these two together to make water, you have to break this apart. So you've got your H and you've got your O2, and it's going to produce water. And this is not balanced right now, so it would actually look like this when you are completely done. Now, you need to know 3 different concepts about energy when we talk about breaking bonds, forming bonds, and then energy in an actual chemical reaction. What's going on there for the total reaction. So again, in the video it said in order to break these apart, you have to add energy. So you add energy to break apart. And the video told you anytime you're adding energy, that's considered to be endothermic. Now, what the video did not go over is why. Why do you have to add energy to break a bond? Well, remember, a bond is an attraction. And if you want to pull these atoms apart, you must break that attraction or overcome the attraction. In order to do that, you must add energy. Okay, so you have to add energy in order to break that. And again, they told you when forming a bond, that is considered to be exothermic. It's going to release energy. So if it's going to release energy when a bond forms, that is considered to be exothermic. Okay, why does that happen? Well, when these join together to form a bond, they become more stable. So they take this energy and they only have to hold on to a certain amount of it to attract. Another way to explain it is when you are forming these bonds, again, you do need energy to hold these bonds together. What's going to happen is it will absorb the energy, but not all of it. It only is going to absorb what is needed to hold those bonds together. Anything extra will be released. Oops, I can't spell. There we go. Okay. Now, as a whole, we need to look at the energy involved in the whole reaction. So you've got energy going in, and then you've got energy coming out. Now, if you have more energy going in than being released, the reaction itself, total, is endothermic. So you typically you're either going to have an exothermic or an endothermic reaction. And again, that's the total amount. So you have to look at everything. So in this case, energy in is greater than energy out. All right. So if you have more energy released than energy absorbed, the reaction is exothermic. So that means energy out would be greater than the energy in. Okay. And you've seen reactions like this. If you have more energy going in than is being released to form new bonds, this would be like those ice packs that we use. Okay. You break the inside, you shake them up together, You mix those chemicals so you get some bonds breaking, then some bonds forming, but it feels very, very cold because it's absorbing energy. It's absorbing more energy than is being released when the bonds are formed. Now down here, when you have more energy released than is absorbed, typically that means you are forming something that's much, much more stable. This is more standard. This is what you would normally see in most reactions. And again, this would be like the burning of the hydrogen in the balloon with oxygen. And then it releases a bunch of heat. Next, we're going to look at bond association energies, the energy it takes to break 1 mole of bonds. It's going to be different for every substance. So let's say we were going to look at water and we wanted to break that apart. Every attraction between different atoms requires a different amount of energy. So if we were to look at an oxygen-hydrogen bond, we would look that up in table 16.3 in the book, and it says an OH bond requires 464 kilojoules for every mole of bonds. Okay, this is the exact same, so this bond would take 464 kilojoules for every mole of water. So if you wanted to break apart all the water molecules in 1 mole, you have to break this, you have to break this. So your answer would be 464 plus 464. And then that would tell you how many kilojoules it would take to break 1 mole's worth of water molecules, which would be 928 kilojoules. Let's look at a slightly more complicated problem. Let's say we had methyl alcohol. That would be CHHOH. Okay. So how much energy would it take to break apart 1 mole's worth of methanol? Again, you'd go to your table, you'd look up your energies. When we look up CH, it is 393, and then that means the CH would be 393, and the CH would be 393. Then you would look up the bond for C and O. To break the bond of CO, that would take 356 kilojoules, and then again, like above, the OH bond would take 464. So how much energy would it take to break 1 mole's worth of all of these? Add them all up. So you've got 393, 393, 393, 356, and 464. Add them all up, and we'll have our answer. When you do that, we get 1999 kilojoules for 1 mole of that substance. And this would be the 10th point on our target. Remember, these values are not memorized. These values are found on a data table. You would actually go and you would look those up.